Thank you for introduction. I'm Masaki Satoh, University of Tokyo. I'm very happy to give presentation on this symposium. So my talk is large ensemble atmospheric and environmental prediction for disaster prevention and mitigation. This is a research project conducted in the Fugaku for 3 years project from the beginning of the Fugaku launched. Okay, the background of the research is as you know, the extreme natural hazard like heavy rainfall or inundation or landslide increasing in recent years. It's thought as a coordinate with global warming caused by human beings. In Germany, you may remember last summer, very flood event. Japan's almost every year, a very heavy rainfall. In US, this is an effect on hurricane. So as you know, these heavy extreme disasters are increasing. So the objective of this research is here to using the facility of Fugaku machine, we do atmospheric weather simulations for using the approach of the very large ensemble experiments and very high resolution experiments to provide probability forecast information with long enough lead time for people to evacuate. And also we use observation big data like satellite data or very high resolution, high temporal resolution radar data. So our research topic consists of 3 topics. Theme 1 is short time and smaller scale forecasting. Theme 2 is global scale forecasting. It's covering a week to several months. And Theme 3 is advanced large-scale data simulation method, including the simulation of environmental air quality simulations. So today's talk shows some topics related to these three themes. First, I start with our Golden Bell finalist study for large-scale, very large and high-resolution ensemble simulation. So this is conducted by Hisashi Yashiro, National Institute for Environment Studies. And then from the theme 1, short-time domain scale forecasting, we show the ensemble data simulation for targeting the heavy rainfall caused in Kyushu area. And then show the we say guerrilla rainfall. We conduct a real-time forecasting targeting guerrilla rainfall in the period of the Tokyo Olympic and Paralympic Games in last year's August. This is by the Takemasa Miyoshi team. And then for the global scale forecasting, we show the large member ensemble for typhoon. This hit in the Kanto area 2019. So all these simulations are very high, very large ensemble, and also very high resolution simulations. And the targeting to the more accurate and more longer lead time forecasting in the future weather forecasting system, targeting for contributing future weather forecasting systems. Okay, first topic is from the Golden Bell finalist study. This is conducted by led by Hisashi Yashiro and the other people listed here. The NICAM is a high-resolution global model we have developed for many years. So global domains, we conduct 3.5 kilometer mesh simulation. This can resolve mesoscale phenomena which cause a heavy rainfall or typhoon in a structure. So very high enough resolution to resolve convective systems. And we in a project, the number 1,000 is a typical size of the member. But there are many reasons for this size of the ensemble, but practically in the forecast, existing forecast system that typically use 100. It's because of a tractable size, but in recent years, many evidence are showing we need more ensemble size. So our study showed that 1,000 ensemble is almost required to better forecasting for ensemble simulation with signal noise ratio comparisons. So before Fugaku started, we have set this resolution and ensemble size, and to make a co-design work between the software and the Fugaku architecture to achieve better performance for this simulation on the Fugaku. So the background of this study is we have a very lot of observations, and also simulation becomes higher resolution to assimilate or to introduce these observation information to simulation. We need to have ensemble assimilation systems. So this is a model, and this is a schematic of the assimilations. So there are many scientific achievements existing before this project. So for example, this is typhoon forecast studies, and also the optimization, and also the like a single precision and floating point systems comparisons, and kernel level optimization and data center design. So one of the issues is we created a very huge data set. So the throughput between computer and storage is very important for this research. So this is a scalability test of the simulation. So for the resolution increases, we have a very stable performance like here. And in addition, we have a mixed precision systems. So from the double precision to mixed, we have reduced the computer performance. And this is for the ensemble size, elapsed time of the data assimilation part is this kind of reduction is achieved. So Nikamai RTF experiment achieved this. This is the world's largest ensemble with data assimilation. We have really conducted this assimilation resolution ensemble member with this 4 trillion grid points, 1.3 petabyte data transfer. So one assimilation cycle will finish within 4 hours. This is 100 faster than the previous K computer. There's no single solution for future high performance with the climate computing. This is we understand from our experience. So we need to recognize trade-offs and promote co-design. Total data throughput and parallelism are important keywords. Okay, then we move to the topic of the theme 1, short range, relatively smaller scale. I mean the Japan or Kyushu area simulations. So this is an ensemble data simulation probability forecast with 1,000 member coupled with a hydrological model using a supercomputer Fugaku aiming to the impact-based forecast. So we had conducted 1,000 ensemble at 1 kilometer grid spacing on the area of the Kyushu area. So this is lead time and the probability, this one. And also we coupled this atmosphere system to the hydrological system. So this system is consists of land processes. So this is result of our experiments. And the experiment setting is we did a simulation with limited area non-hydrostatic model with some Kalman filter approach. So this is inner core and outer simulation cycle is 5 kilometers. And 6-hour cycle is used. This is the same as a JML operation method data simulation system. Then forecast is 1,000 member with 2 kilometers. So we conducted the July, this is May season in 2020, Kyushu rainfall. So this is radar observation. We are radar observation. This is Kyushu area. This is the time. And the later time, we have a very high resolution, high precipitation here. So previous JMA system use a deterministic forecast. This is rainfall is forecasted, but very longer than reality. And in later time, this main region is over the ocean region. This is something deviated from the reality. In our probability forecast system, the area in rainfall is located in Kyushu area. This is closer to the observation. And this later time, we have a more better forecast than the deterministic systems. So this is we show the difference impact of our large ensemble simulation system. So please note, this is probability forecast. This is a unit of the percentage. So we may have a percentage forecast. In this Kyushu area, we have a high probability of heavy rainfall. We may say Senjo Kosuitai may occur in in a half a day or longer hours than the present forecasting systems. So this system is coupled to the hydrological ensemble simulation. Then we can forecast the flood in along the river. So this is a probability forecast. This observation show the flooding area, and the probability. This show the color of this probability of the flooding. So this show the 1 hour before the flood and just around the flooding time here. So to summarize the result, this is time, and this is probability, and this is flooding level. So this is a level, highest record level. So this show the observation show this is very dangerous time. So deterministic forecast show here the probability of the handcast records show this kind of values. So during this period, we have a very high probability of the flood. So we are using this system, we could give information of the high probability of flooding. Okay, next topic is a guerrilla rain forecast using Fugak system. We have conducted July to August last year. So this we are really using Fugaku and conduct real-time forecast and produce the data set results, and this is provide to open Riken system and collaborate public company using the smartphone appli. So this is an example of the rainfall in the Tokyo area. So we conducted this real-time forecast using 9% of the Fugaku resources. Ensemble size is 1,000, and using this system. We did last year, but in comparison to last year, we have increased this ensemble size and resolution. This is because Fugaku is more powerful than previous year. So the observation data for using this one is we have a phased array radar. This is very high resolution, three-dimensional rainfall captures. This is located in Saitama area. And yeah. Then this data set is observation conducted by NICT, and this is transferred to Fugaku. And the system with numerical model with a scale LTK. This is developed by Riken. And then the data set is open from the Riken homepage and also the smartphone applications. These are real-time data workflow. So we have a lot of meeting with the Fugaku administration teams and researchers. So we made a very detailed scheduling for using Fugaku, using more than 8,000 nodes. So these are example three-dimensional observation and simulation. So assimilation, using assimilation, we have a more realistic result. So these are examples of the rainfall for observation and forecast we have conducted. We are now living in this Kashiwa area here, so we experience this rainfall and we see this result. We can forecast these things. So this is another example. So again, in two months, we have demonstrated Fugaku really. We really use Fugaku and did real-time forecasting, and data are provided to the communities, societies. Okay, the last topic is large ensemble members simulation of extreme events, Typhoon Faxai, by using NICAM with 14-kilometer mesh. Again, in this case, we conducted more than 1,000, actually 1,600 ensemble simulation for targeting the tropical cyclone Faxai. You may remember this is 2019. We have this is the ensemble of the forecasting the typhoon location typhoon. We did several weeks before the typhoon landfall. So this is a simulation results. Some members typhoons. In the reality, typhoons are coming like here and hit Japan. But in these ensembles, we have some good tracing the real typhoon tracks, but some deviate from here, location and timing. But the majority, we have, on the average, we have a more realistic simulation. So, but we use this 1,600 ensemble data, the possibility or mechanism or typhoon forecasting with several weeks before the landfall. Okay, this is a summary of our result. Lead time 0 before the lead time the landfall. This is 2 weeks before the initial time. So this shows this is a number of typhoons simulating Faxai-like typhoon. We have defined we have calculated the deviation for the real typhoon and simulated typhoon and defined the metric for the Faxai-like index. So using this index, lead time, at some point, we have an increase of the more probability of typhoon. Just around 7 or 8 days, we have an increase of the probability. Lead time 0 means the genesis day observation. Lead time 15 is August 20. So this is the genesis. I mean, the genesis are around these locations. So among the 1,600 simulations, Faxai-like typhoon is captured about more than 600. So more than 1/3 is Faxai-like. 70% simulation Faxai-like typhoons. Lead time 8 days. In the case of lead time 8 days, lead time means 8 days before the genesis. So increase during the lead time between 8 and 11. So this is all the member of typhoon simulations. So red means more Faxai-like, and the colors show the deviation of real typhoon Faxai. So the mechanism we found is what happens between 8 and 11. So this lead time 6 means 6 days before the genesis of typhoon, and 7, 8, 9, 10. And 11, 12, we have something different between 8 and 10. So this is reality in the observation. So this yellow area show the height of the geopotential height of the reality. So this yellow area is captured in this timing. But this another vortex coming before the 10 or 11 days. So we understand the smaller vortex is important to tropical cycle genesis. So in this lead times, we have successfully reproduced this smaller vortex. This causes a tropical cyclone genesis. Well, before that time, another vortex is coming. So even Faxai-like, but this inhibits the more realistic genesis from the typhoons. So this result indicate the types of vortex or the precursor of the typhoons important to more closely, more accurately predict typhoons. So this also show the genesis limit of the genesis possibility of forecasting. Okay, this is results of Faxai ensemble simulations. We successfully conducted a 1,600 member ensemble simulation for typhoon Faxai by 14-kilometer mesh NICAM on the supercomputer Fugaku. The number of members with simulating Faxai-like typhoon were increased between the lead time of 11 and 8 days. The increase in the success member might be attributed to the improvement of retribution upper tropical trough in the simulation between these lead times. Okay, I introduced all the topics. So this is summary slide. We are now at the end of the second year of this project, large ensemble with atmospheric environment prediction for new area of disaster prevention mitigations. So from the Gordon Bell result and the topics we showed today, we understand we open the door of global very high resolution, very large ensemble weather simulation, as we have never seen before. Petabyte scale high performance data analysis is required. And we show that successful co-design between the state-of-the-art supercomputer and real-world applications, and the importance of data-centric design of the application in the exascale area. So we have shown some cases with the Southern Ensemble experiment to improve forecast accuracy. One is a heavy rainfall in July 2020, Kumagawa River flood. Typhoon Faxai in September 2019, and real-time guerrilla rainfall forecast using Fugaku in last summer. Okay, that's finishing my talk. Thank you very much.